Number 5, speaking of things that are far away, you all love whipping out your Nikons so much that I wouldn't be surprised if a Nikon executive dreamt up the entire flat earth hoax as a viral marketing campaign. If a Nikon executive dreamt up the entire flat earth hoax as a viral marketing campaign.
They're on to me, dude. Those guys are sharp as nails up there. You can't put anything past them. Oh my God, dude, I'm freaking out. I am so stressed out. I feel like I'm having a panic attack.
You want to talk about stress? You want to talk about stress? Okay? I've stumbled onto a major company conspiracy, Mac. How about that for stress?
Dreamt up the entire flat earth hoax as a viral marketing campaign.
You've lost your mind.
Viral marketing campaign.
You've lost your mind.
You take a boat that's far away, pull it back into focus, and then marvel at your own brilliance for figuring out how to operate a camera. Well, try this one then. Stay on the boat. Don't cut away. Stay on it until it disappears. How will it disappear? Bottom up, just like everything else. I wonder why you've never put that on YouTube. Bottom up, just like everything else.
Okay, Charlie, I'm gonna have to stop you right there.
Bottom up, just like everything else.
Look at another example of diffraction limit. The lid in this example in a warehouse is marked at 1-inch intervals. The observer height is 1.5 inches. The pictures are taken at 20-foot intervals. So this is a fixed height changing distance example as opposed to a fixed distance changing height example. So taking still shots of the video capture here, or the picture capture, we have 100 feet, 140 feet, 180 feet, and so on all the way to 460 feet. And you can pull these objects out and compare them to one another between the 460 feet and 100 feet, which there is very little to no angular resolution loss at 100 feet. And so if you overlap the two with the scaled paper of 1-inch intervals in between them and mark out the horizon line as the point of the inferior miraging effect, then you can see that you have lost approximately 1.75 inches at 465 feet. And again, you can use this to then calculate theta for this particular wavelength, diameter, aperture camera. So we'll do that here. So again, this 1.75 inches is lost at 460 feet. So we plug in 1.75 inches as our height, which is 0.1458 feet across a distance of 460 feet. Using our same diagram as we've done before, solving for theta gives us a very similar angle to what we've gotten before, which is 0.018 degrees, very close to our 0.02 degree arc minute, 1 arc minute human eye resolution limit. So using the loss to calculate theta for this camera within these conditions, I can now calculate the amount of loss over any distance. Alternatively, I can calculate the amount that is resolved with a change in height, just like we did before. So plugging in at 260 feet, I would expect a loss of about 1 inch. At 380 feet, I would expect a loss of 1.43 inches, and so on. If theta is held constant across any similar triangle, we can restate our formula as h1 over h2 equals d1 over d2, right? And those ratios then could correspond to one another across tangent theta as h1 over d1 equal to h2 over d2. So if you know the distance to an object and the amount that is lost across theta, you can calculate when the object would be completely lost. So for us, our 11.5 inch height lid completely disappears over the horizon at a distance of 3,050 feet, or 0.57 half a mile, give or take. Alternatively, over a distance d of 1 mile, 5,280 feet, we would lose a height of 1.65 feet or 20 inches. Of note, if this lid were instead a 6-foot man, he would disappear at 3.6 miles within these wavelength and aperture conditions. Again, this is an optical phenomenon, it's not physical curvature. The lower horizon limit has been met, the compression rate has been met below the eye line or below the aperture or below the eye line of the camera in this case. And so the upper aspect with distance is going to set into that line. As another example, you can see the effect more clearly here. The lid is marked at 1 inch increments and the photographed and is then photographed 1.5 inches off the ground at various distances away. So some of the pics were downloaded at different levels of zoom, but you can see the effect on the lid. It disappears into the floor and the whole lid is brought downward. You can see the lines on the lid gradually merge with the floor, and I've outlined those markings and placed them against the purple line. You can see that you start to lose them all sequentially as with greater distance. So let's summarize where we've been up to this point. I want to impart to you that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction phenomenon. So option 1, again, the ground is brought to your eye level. The person disappears from perspective by walking straight away and vanishing bottom first from things getting smaller with distance and an angular resolution limit. And here's some of the examples that we've gone through to this point. We have our lid disappearing into the floor. We have some calculations that we can use to determine our horizon distance and or loss rate with height change. So for example, at 100 miles, we expect to lose roughly 184 feet by angular resolution at 0.02 degrees. But with curvature at 100 miles, we're losing 6,660 feet. So the takeaway is that with distance, diffraction plays less of a role than refraction does. That's the takeaway here, because we do see the bottoms of things lost at a greater rate than simply 184 feet at 100 miles. By extension, the use of infrared camera technology is very useful over long distances since it is more prone to diffraction issues but experiences less refraction at the same time. So because refraction does play a decent sized role, that the infrared camera technology is proving to be a very good tool to view these distant objects, which again do not have anywhere near the expected rate of loss, such as 6,000 feet of loss at 100 miles. It just doesn't exist.
Bottom up, just like everything else.
So our rate of curvature is 6 feet lost at 3 miles from a 6-foot observer height. We need to approximate the angular resolution limit line within our curve as close as possible. We only have 2 crossover points, one at 0 miles and one at 3 miles. we know that the size change must be exponential within perspective in order to get a curve to develop out of it. Can't be linear. So we will solve for the Earth's radius by knowing the arc length and arc angle. You can see here we've just taken our two triangles, placed them against a curve for a person walking over at that rate of 6 foot loss over 3 miles, and we have then extrapolated it along a greater circle. So the observer would assume they are watching a person descend from their point of view across 2 theta at 3 miles. The first theta, 0.0216 degrees, would represent the observer height at 6 feet until reaching 0 feet, and the second theta for the drop from 0 feet to -6 feet. So we can therefore take our arc angle of 2 theta across an arc length of 3 miles, or we can take the drop rate of 12 feet across 3 miles. Either will give us r for the greater circle. We can now solve for the radius of Earth from the angular resolution limit of the eye as our segment here with r along the radius, or along the one aspect of the triangle, and 3 miles as our opposite end, and the angle being across 2 theta, which is 0.0432 degrees. That will give us one number, and the alternative is to use the ratio of 12 foot over 3 miles is equal to 3 miles over r. Both will give us the numbers listed below. So we get for one number 3,978 miles, and for the other one 3,959 miles, giving us an average of 3,969 miles. So for our circle based on the angular resolution limit of the human eye, we can calculate a radius of 3,969 miles, and the circumference then comes out to 24,938 miles. And coincidentally or not, the Earth's radius is said to be 3,963 miles with a circumference of 24,900 miles.
Bottom up, just like everything else.
I'm gonna have to stop you right there.
So for our circle based on the angular resolution limit of the human eye, we can calculate a radius of 3,969 miles, and the circumference then comes out to 24,938 miles. And coincidentally or not, the Earth's radius is said to be 3,963 miles with a circumference of 24,900 miles.
Just like everything else.
But I have a question for you then.
Sorry.
If
before
you
do,
have
why
a
is that in the
100-meter
calculator?
tall building,
Why isn't that in the calculator?
it's generally not needed.
Sorry, you've just explained that stuff disappears with distance based on its angular size, and now you're saying it's not needed. The calculator will simply assert that it's Earth curve that's causing it. Well, it's not.
It is.
The angular size is causing it. You've just made that clear. Calculable in the Rayleigh criterion. And it's not included because it's not needed.
Nathan, I do not.
It is
I do not
needed, and you're
agree
talking
that
over me. I'll just shut you up. Yeah, that he's now going to argue the toss about Ranty about isn't included in the curve calculator. So anything that disappears with distance, according to the curve calculator, the only cause, the single cause, is Earth curve. Sod all to do with what he's now about to argue with Ranty about. It's not included and not needed according to him, even though it's very real and how we see things.
It has nothing to do with it. And
Sorry, I'll just do it again. This tree on screen takes up 50% of the frame, and I absolutely guarantee if it was 1,000 miles away you would not see it because it was too small. The calculator would say sod all to do with how small it is and only Earth curve obstruction. Well, that's simply not the case.
Correct.
Things get too small. Not correct. Things get too small to see regardless of your fundy belief in Earth curve. So, yeah, there are multiple reasons why things can disappear into the distance, and you can only claim Earth curve obscures them. Wrong. Things can get too small, and you can't resolve them. Nothing to do with Earth curve, completely ignored in your calculator. So will we have a long, prolonged pause and then you ignoring exactly what I've just said and then claiming victimhood when I point out that you've ignored me for the third time?
No, I'm just giving you dead air time to give you a chance to think about it and reset a little bit. and
Think
then
about what?
get ready to listen.
Think about what? You've just immediately ignored all angular relationships and started using the feet and inches value, actual sizes. So are you going to address that, or just have a long, prolonged silence and claim, I've got to think about something?
Yeah, I'm going to address it directly from angular perspective or angular size.
It's not included in the Earth curve maths. There is only one cause, Earth curve. So you saying you're going to address it, how the hell are you going to address Mick West and the Dizzy Hub and the Walter Bisling calculators that all exclude this? Are you going to magically undo that?
I'm going to show you why it isn't necessary. But
Oh, so we're not going to include it then. So we've immediately done the quick switcheroo, which is say that you're going to include it, and now we're going to detail why it's not included. It is absolutely required.
It is absolutely required.
We see in angular size.
We see in angular size.
The further something is, the smaller its angle, and the more likely it will eventually disappear from our view due to its angular size.
Due to its angular size.
Something that you are now going to try and attempt to dismiss. Has he just buggered off? Has he run away?
Yes, I think he dropped.
Yeah.
He had to go to work.
Oh, really? Yeah. At the point that I'm absolutely obliterating his argument because he can't include angular size. The calculator's hijacked perspective. So there's never going to reach a point where he says, okay, I'll do the angular size, making it seem to the audience like he's going to insert angular size and do the calculations using angular size. No, he'll do a load of angular size maths and then ignore them completely and go back to actual sizes. Sizes that don't change with distance. A 100-foot building will be a 100-foot building if it's in the near foreground and it's taking up the entire frame, or it's too far away to actually resolve it at all because the angular size is small. It'll still be a 100-foot building according to Bob, and that's how he'll run the maths, because that's what he needs. He needs the effects removing from the calculations. He'll just say the 100-foot is 100-foot, even if it's 1,000 miles away. That's what the trick is. Hijack perspective by using actual size when we see an angular size.
That's what the trick is. Hijack perspective by using actual size when we see an angular size.
Bye-bye, Bob. Total failure.
Bottom up, just like everything else.
You've lost your mind.
The following experiment will demonstrate that what we perceive as curvature of the Earth due to its spherical surface may actually be atmospheric phenomena occurring over a horizontal surface. This experiment can be conducted on various level surfaces, both indoor and outdoor, basketball courts, tennis courts, ice rinks, and so on. It can even be conducted over small ponds and bodies of water. These observations show that a spherical surface is not necessary in order to witness objects disappearing from view bottom up. Theoretical curvature cannot be pointed to as the cause for the apparent sinking in the experiments presented here, as these observations all take place within 600 feet, which is not enough distance for any of the said curvature to be present at all. We will also demonstrate that, from a distance, the bottom floors or layers of buildings and structures also disappear because of atmosphere over a horizontal surface, not disappearing behind a curved one. We will be using a scale of 1 inch equal to 5 feet. Our viewer height will be 1.5 inches, so 7.5 feet to scale. These observations are being made over small ponds, which produce small waves, accurately simulating the waves seen when boats sail on the ocean in large water. A wave of about an inch or so on our experimental ponds would represent an ocean wave of approximately 5 feet. This first observation was made on July 24th, and the temperature was around 82 degrees at the start of the experiment. The blue toy boat represents a boat that's approximately 30 feet long by 8 feet tall. The yellow and orange boat represents a vessel that would be 25 feet long and 15 feet tall. During the hottest parts of the day, the boats disappear hull first while moving away from the viewer and camera, but they do so above the apparent horizon. This is to be expected due to the variation in temperature of the air and the temperature of the water. As the evening presses on, the temperature in the air cools down, and the boats begin to disappear hull first at or below the apparent horizon. Next, we'll see objects that are set up across the pond to represent a distant city skyline. Like the larger buildings and structures whose bottom layers are no longer visible, seeming to be sunken below the ocean horizon, these objects will also be missing their bottom layers. This rough miniature skyline is placed approximately 550 feet away from the viewer or camera, which is 6 1/4 miles away to scale. With the viewer height of 1.5 inches or 7.5 feet, we can expect to be missing just over an inch from the bottom of the skyline objects, representative of about 5.5 feet. Notice how when we view the skyline from a higher vantage point, all of the objects are in view. But when we go down to the water surface, most of the objects are no longer visible. Reminder, we are not merely seeing these objects from a higher view because we are raising above a curve, and they are not disappearing behind a curve when we drop our view. This pond is too small for that to be the case. Notice the dramatic disappearance at the bottom of the objects after just a slight change in viewer height. This observation takes place in 27-degree temperatures and will include another toy boat and representative city skyline, this time with the boat sailing to the skyline objects. On this day, the cold air above the warmer water causes miraging and lots of atmospheric distortion as the boat sails off. This last observation takes place on a clear day at 38 degrees. Because there isn't extreme variation in temperatures between the air and water, we see the boat appear to sink below the horizon. The boat is completely out of sight while it sails by the skyline objects, with only its water trail visible. Rising up allows us to see both the bottom of the skyline and the boat sailing in front of it. To summarize, what these observations show is that what we perceive and call curvature of the Earth isn't actually physical curving of the surface, but rather we are witnessing the bending or curving of light through dense layers of atmosphere over a horizontal surface such as the Earth's oceans and lakes. We expect light to travel in straight lines, but we know that light travels slower in denser mediums, creating the illusion of curvature.
Well, try this one then. Stay on the boat. Don't cut away. Stay on it until it disappears.
Let's see what we can see. Can you guys see that? Doesn't look like it's going over the curve to me. In actual fact, it looks like it's got a massive inferior mirage both at the front and the back. You can see the inferior mirage. See at the back there, you see that white bar? And the mirror underneath it? And what's going to happen now is that boat is going to go further and further and further away. That inferior mirage is going to stay at the same angle, but because the boat gets smaller, it's going to end up further and further into that inferior mirage, and that's what's going to block out the boat eventually. But hopefully we're going to see a boat go over the curve, guys. That's all I see. Inferior mirages. Can you see how the C on the truck is being stretched down as well? That's very interesting. True, no one's ever seen a boat go over the curve. Absolutely correct. It's interesting now that the wording is almost blended into nothing. Oh, look at the inferior mirage, guys. Look at that white being reflected underneath the blue. You can still make out the words, roughly, but look at it turning into an inferior mirage, guys. Oh, look at that. Did the boat have a mouth before? Did the boat have a mouth at the front before? Look at the stretching going on that, guys. Does this... Right, you know when you've seen this image, this presentation of them showing you a boat go over the curve, they literally have a little model of it. Do you remember? You know the one I'm talking about, where they flick the boat and the boat goes behind some, you know, obstruction, and it's supposed to be representative of this is what it looks like when a boat goes over the curvature of the Earth. Well, does that look like anything like the boat that you just saw, we just followed? And they'll have you believe this is going over the curvature of the Earth. Well, if that's the case, then why does it end up all distorted? Why does it all end up blending into something completely different? You know, how does it end up starting off looking like a boat and end up looking like a smudge? You know, I'm filming this in 4K, guys, so I will release this video later, so you guys can watch it for yourself. I'm filming it live through the viewfinder so that you guys can get a glimpse of what's going on, but you'll see it better in the 4K video that I'll put out later. So I'm still not seeing any boat go over the curve though, let's put it that way. All I'm seeing is things stretching, warping and going behind that inferior mirage. Not seeing it going over any curvature though, guys. I'm seeing it turn into an inferior mirage. Yeah, wait, I'm going to do a presentation on Nathan soon as well when I get back. I found something out that was hidden deep in Red Rhetoric's video about the apparent curvature of the Earth, the boat going over the curve apparently. Well, we're going to debunk that. Oh, and one other thing. He inadvertently proves that the inferior mirage does hide compression, which is fantastic. I mean, I've been looking for that myself, but to find it on Red Rhetoric's video with him saying it's proof of a boat going over the curve was just brilliant. You know, imagine looking into this guy's work and seeing something that's so special to flat earthers. It's like you now know when you look at the inferior mirage you're going to be seeing compression behind the inferior mirage, and I can prove that. I can prove it. Seeing it go over the curve, guys, but I'm seeing it go further and further away, and I'm seeing it end up getting itself inferior miraged into what looks like some kind of shark or something now. As you know, I quite like names of different sharks, shark boat, all that kind of stuff. And right now it looks like it's got a big fat mouth at the front. It didn't look like that when it set off though, did it? Keep on recording it in 4K. So this is really interesting stuff. I mean, this boat now must be perhaps 10 miles away right now. Have we got a time right now, please? Oh, 12:21. So it's 12:21. So we can track this boat, and it must be about 10 miles away at least now. Elevation above sea level 3 feet. Well, sea level. I say sea level. See where the water's actually lapping up there. Wow, you can actually see the swell here, guys. I want you to look at this. Still not seeing it go over the curve. Oh, sorry. Yeah, it's just outside of Blackpool, mate. It's not the right season for curvature, no, it sure isn't. Still watching it fold into nothing. Everything's being miraged down on itself. And all we're seeing in this is the boat going further away and ending up in that because it gets smaller with distance, it's going further and further away, and it's by virtue of that it's getting closer to that inferior mirage band. I mean, it's almost disappeared right now. The inferior mirage is almost complete. You can see where it's joining up. Do you know what's really going to be so frustrating right now? Is that we have a massive buoy right in front of it as it's just about to disappear. Ah! Oh shit! Oh no, it's gone! Bloody hell. And the reason it went is because Oh no, no, it's still there. Just.
Stay on the boat. Don't cut away. Stay on it until it disappears. How will it disappear? How will it disappear?
Okay. Now. Yeah.
How will it how will how will it disappear?
How will it disappear?
How will it disappear? How will
Oh, look. You can have it.
How will it
how will it
Sorry, your peanuts have disappeared. I will download more. Meanwhile, have a banana and some milk.
How will it disappear?
Holy shit, Batman. Superman refraction. Cutter's Rock. Look at that. There's Cutter's Rock. Sure as shit out there. That's Cutter's Rock. Look at that other boat way out there. Holy crap. There it is, look at that. That's a big old boat. Way, way behind Bayport. There's Cutter's Rock. And look how far back you can see the water. Behind that boat. Or behind that rack. Wow. Wow. Let's do this again. Holy shit, Batman. Superman refraction. That boat should be way underneath the curvature of Earth.
How will it disappear?
How will it how will it
I like studying these mirages too, because what we see on the roads and over the water are pretty much identical. You know, and this to me is also, not only do you have light distortion, but you also have heat distortion. Obviously, you can see all the images are wavy, wiggly, squiggly. And the farther away these objects get, as you can see, like off to the right with the power lines, you can see how much more squiggly they get and more distortion they get. Also pay attention to the reflectors down the center of the road. You'll see the one at the top, at the very top of the hill, always seems to want to get, it goes in and out of visibility. And why is that? Because things are being obscured. Things are being hidden right here. And obviously you can tell that the last two disappears and then they pop back up. Also, if you notice, these are red reflectors. You should be able to see the red all the way down through there, and you are not able to see the red. So something is being hidden in with this mirroring effect, this miraging. Also, where is the top of the road? Where does the actual top of the road end? And this part here, this little part, I had sped up 2 times the speed. And then what I'm going to do is I'm going to lower my camera down even lower, down to the 28-inch mark, right here. And, you know, I kind of get a little out of whack here, of course, because I'm, you know, lowering my legs of my tripod, not my little short legs of my body. And of course, you know, I'm kind of all out of focus here because I'm looking straight down, trying to get the camera set. And I kind of wanted to put this in to show that I was lowering my camera down. Obviously, you can tell I'm doing something with it. But here you can really tell I lowered it because a lot of the reflectors have vanished completely. And this is what I say. Where does the road start? Where does it begin? Because some of that road is, I mean, definitely hidden within the mirroring, right? So it is hard to determine exactly where the road actually begins. And if you ask me, part of this road is being ramped up over. The light is actually causing a ramping up effect, so you're not actually seeing the road. Obviously, you're not seeing the road. Plain and simple, folks. You are not seeing it. It's not there. But as the cars emerge over a hill, because this is, I'm looking up a hill, you do eventually see the car. Now, where you see the car at, is that exactly where everything's at? I mean, is that where the road is actually at? No, I don't think so. I think part of that road is still being blocked out. It's being hidden by the optical effects and also the distortion. So I look at this one picture here. I took a screenshot here coming up shortly of one of the cars just as it's coming up over the hill. And you'll see it coming up right here. And I drew a line across there approximately where I think the road should be.
How will it disappear?
Okay, do it. Oh!
How will it?
You can see it right here, the layering, the mirroring, all in there. And you know, that really does affect our vision. I mean, look at this. This is what I'm talking about right here. You know, you don't see it, but it's there. And it's further out too, where everything's just being mirrored. And this is what I try to show all the time, how this affects our vision, how it affects how we see. You know, it's just a whiteout. When you get farther out there, everything's just blending in together, mirroring. And you can see how this is not refraction, lifting shit up, doing shit to anything. This is just the calm water. Okay, look at right here. This is what I'm talking about right here. This is a good example of calm water. See how it I mean, just everything right here. Look at it. You can see it. Well, open your eyes. It's not refraction. It's a reflection. And, you know, this is a perfect example right here of how that works. People can say all they want, but that's it, right there. I'm gonna let it set right there. Maybe even back out a little bit more. Give you a good view of that. Right there. See it? If you don't see it, you're blind. That's all I can say. If you don't see it, you're blind. And what beyond is doing the same thing, just mirroring the sky until you get to the point where the actual convergence is. You see it? Or are you blind?
How will it disappear?
Or are you blind?
Do I really have to say it?
Say what?
Yes, Kate. Say what?
You need glasses.
And where is his glasses? He can't see without his glasses.
How will it?
You don't think that water can be like that farther out beyond it due to my camera's ability to resolve that edge? Look at it. Changes all the way across. And that's what we try to get across to you. That this horizon line changes constantly. Constantly, people. Constantly.
How will it disappear?
How will it disappear?
I shouldn't be able to see that boat that's going behind the Bayport bird rack right now at all. That whole boat should be gone because that boat is well past the bird rack. But he only looks like he just passed right behind it. But that's the illusion. And the definition of mirage, it does say not to believe your eyes. So maybe we shouldn't believe our eyes or our ears that we hear when somebody says that it's refraction. That's the culprit of pulling everything up from behind the curve and placing it perfectly in front of us in the water. This is what I find when I'm doing my long observations all day long. Sometimes this horizon does change, but I see it more as a change due to the mirage. And from part one, you can see what mirages can do. It never pulls things up. It appears to pull things down. Plus, it also appears to block things out and cause a ramp up so we don't see what's farther back there. Now look at this boat. It is perfectly in the water, and you can obviously tell that it is not being refracted up. It is in the mirror, the mirroring water. And that is what hides a lot of stuff. On top of perspective, lensing, angular resolution, and all of these things play a factor in how we see. So I hope you enjoyed my presentation, and I hope that people with the eyes to see and pay attention to detail can tell that the earth is not curved out there. It is actually an illusion of a curvature.
How will it disappear?
So if you know the distance to an object and the amount that is lost across data, you can calculate when the object would be completely lost. Again, this is an optical phenomenon, it's not physical curvature.
How will it disappear?
Wow, you can actually see the swell here, guys. I want you to look at this. Swell here, guys. Swell here, guys. Swell here, guys.
How will it disappear? How will it disappear?
Now?
Yeah.
How will it? How will it
do it?
Oh!
Sorry, your peanuts have disappeared. I will download more. Meanwhile, have a banana and some milk.
Dreamt up the entire flat earth hoax as a viral marketing campaign.
You've lost your mind.
The weakest link. Goodbye.
Speaking of things that are far away,
That is just impossible under the globe model. 43,848 feet should be hidden behind the curvature.
There's data points even beyond 540, maybe 600 miles out.
Dreamt up the entire flat earth hoax.
They're onto me, dude. Those guys are sharp as nails up there. You can't put anything past them.
Goodbye.